for the current presentation, I am here to introduce my colleague, Ali Madani, who is the leader of machine learning at Cyclica, and he's here today to talk about filter and transfer learning, which is a neural network approach that allows us to take advantage of multiple tiers of confidence in data. So Ali, when you're ready.
Elena, for the introduction. So let me share my screen. So good morning, everyone. I'm Ali Madani, leader of machine learning at Cyclica Incorporation, and I want to talk about the concept we worked on recently, which is about deep learning across label confidence distribution via transfer learning. But let me introduce us first. Cyclica is a Toronto-based venture backed by a technology company that has built and commercialized an integrated AI augmented drug discovery platform that embraces the complexity of disease to accelerate the discovery of better medicines. So this is what we do in general, but if you are interested to know more about us, you can follow us on LinkedIn to check our technologies, to check the collaborations we've had and successful projects, or any available job opportunities. Also, you can reach out to me on LinkedIn, and I will be happy to answer your questions about our technology. But let's check one of the technologies, and it's called Ligand Express. So what we do in Ligand Express is about drug discovery, so drug-target interaction prediction to come up with a holistic drug design scenario. But Ligand Express is powered with a deep learning engine called Matchmaker. So the talk is related to Matchmaker, although I will focus mainly on the scientific part of the deep learning model we developed. So what Matchmaker does, it tries to combine ligand information with pockets information in proteins. So those are parts of proteins that ligands can bind to, and those ligands can eventually, potentially become drugs. So we combine these features and we put it in a deep learning framework. So we train a deep learning model using all this information and millions of drug target interactions. And it relies on combination of structural and experimental data. And we could achieve high accuracy, high generalizability, and high throughput. But it was not only successful because of deep learning. We could achieve high success in our purpose because of combination of deep learning and our proprietary data engineering and featureization, which is related to 3D protein structures. So we needed to combine our domain expertise and knowledge with our deep learning expertise and knowledge to come up with a good platform, to come up with a good technology, and eventually try to predict drug target interaction, which is the goal of Matchmaker. But there was a traditional problem in the field, and it's about confidence. So it is a traditional issue in our field, our domain, and many other domains. But let me first explain what I mean by confidence. So here we want to talk about label confidence. So we know that we have different ways of annotating data points, annotating different data points for classification setting or any other scenario that we may have. And it can be done in different ways, and all of them could result in different levels of confidence for the labels of data points. We can have labeling by multiple experts. For example, radiologists or pathologists try to annotate images or parts of images, but not necessarily they will always agree with each other. Imagine you ask 20 radiologists to annotate 1,000 images, 1,000 different parts of images. For some of those parts or for some of those images, they may all agree with each other. So 100% confidence. Perfect, awesome. That is the ideal case. But that doesn't happen most of the time. Sometimes we can see that one of the radiologists doesn't agree with the rest. 4 of them don't agree with the rest. So, and that causes the difference in the label confidence, which means that for some of the images, we are 100% confident that there should be a tumor in that part. But for some other images, we are maybe 60% confident. And then we have to use these different data points with different levels of confidence within a machine learning or deep learning model. But it is not restricted to expert annotation. We can have labeling by non-experts. Imagine we ask people, non-experts, we are not animal experts, so ask them to annotate images of animals, and we ask them to somehow separate jaguars from leopards. So that will not be that successful, because even before I put this presentation together, I couldn't identify jaguar, discriminate jaguar from leopard that easily. And that's a problem, because that also increases the likelihood of lower confidence for some of the labels. Yeah, we can easily discriminate cats and dogs, but some of these discrimination will not be that easy. So there could be mislabeling for some of these images, therefore decreasing the confidence we have for the data points that we want to learn from. But these scenarios, so these images are very easy to talk about because we can visually see them, but we have some more complicated issues and some more complicated ways of having different confidence level. One of them is experimental measurement. So for measuring any physical, chemical, or biological phenomena, we have different technologies, different assays, and we have experimental people, experimental experts doing those experiments, read the results, and report them. But there is different levels of confidence in each one of these steps. So the technologies and assays are not perfect. We know that. We are human, and we are not perfect. And we know that too. So combining all these issues, we get different levels of confidence for data points. But that's not the only problem. Sorry for the blurriness of this picture, but IC50 is a summary measure of how a drug or ligand affect a living cell. If IC50 is lower, it's better. But imagine we want to build a classification model. So we should use a cutoff and saying that, okay, if it's below this cutoff, perfect, it's positive data point. It means that the drug is working, the ligand is working. And if it's above that, it means that it's not working. Okay, but you agree that it's a continuous variable. And when we want to build a classification model out of it, these continuous values will be dismissed. So we can use those values as some sort of confidence for the data points. But the question is how we can use them. And last but not least is labeling based on literature. And it's a very known problem. People try to use text mining and different, more advanced technologies recently to come up with, for example, labeling drug target interaction from literature or any other physical, chemical, or biological phenomena out of scientific literature. But we know that when we mine text, articles, blogs, we are not confident in the same level for all the data points and all the extractions. So we have different levels of confidence for what we extract from literature and from all those texts, canvases. Okay, good. So we know what we want to talk about. We are talking about confidence in labels, in data points. Yeah, this is a very known problem to deal with feature noise or if there is any sort of uncertainty on the features, but we have this problem of label confidence as well. And it is a traditional problem in drug target interaction because the public data sets that we use and many other companies use have different levels of confidence for any data point, any interaction reported in their database. Okay. So that's good. But what we know is in deep learning or in machine learning in general, we want to have more data. More data, better, but it's not that easy. We want to have more high quality data. So it is not only about increasing number of data points that we don't know much about them, but it is about having high quality data, but preferably high quantity as well. But we know that usually we have a quality-quantity trade-off, which means that most of the time we have data sets, and each data point has different levels of confidence. So if we want to use all the data set, so increase quantity, we will lose on quality because the average quality will be low. Or we can go for higher confidence part of the distribution, the data set. But in that case, we will lose. We have to throw out a ton of data. So there is a trade-off there. But the question is, could we somehow benefit from both parts, quantity and quality, without restricting ourselves to this trade-off? So let's first have a visualization, have an illustration to understand why lower quantity or lower quality could cause some issue when we try to build a machine learning model. Imagine we have a two-dimensional space, two features. Very simple example. Sorry if it is very simple for you, but it is good to make sure we are all on the same page. So it is a two-dimensional space. We have enough number of data points. Enough is not a quantitative word, I know, but we understand all what I mean. So we have enough number of data points and we have high quality labels. We could easily come up with the decision boundary, and we know that classification is all about decision boundary identification. But imagine we have two cases. One in which we have low quantity, so lower number of data points. One problem, one issue that can happen is because of lower number of data points, we are not covering all the space. That can happen, we know. It is possible that we cover all the space even with lower number of data points. But imagine we have this example that we don't have data points for part of the space. So our decision boundary will move. And because of this shift on the decision boundary, that decision boundary will not be generalizable, because we know that this should be the decision boundary. This should be the decision boundary we like. But this decision boundary worked maybe perfectly even in training set, but it is not generalizable. And we are prone to overfitting because of lack of data points in parts of the space. But another scenario that can happen is lower quality. So the issue is not always about quantity. Sometimes it is about quality. Okay, so what can happen is we may have mislabeling even close to decision boundary, but that doesn't matter. The decision boundary could be even close to the real decision boundary, but our confidence for that decision boundary is lower. So this is a very, very, very simple example. And we know that in deep learning, or even in some of the classical machine learning models that we build, it is much more complicated. And it was only an illustration of what's going on, why lower quantity or lower quality could cause some issue when we try to train models. So we have this trade-off. We have quality-quantity trade-off. We want to have higher quality. At the same time, we want to have higher quantity. But traditionally, one way of dealing with these different confidences is to just coming up with a cutoff, throw out low confidence data, but that's not good because we are benefiting from higher quality. We are not benefiting from higher quantity. Okay, so we want to somehow benefit from both. And the question is, how could we do that? How could we benefit from both higher quality and higher quantity? Okay, is there any question before I go through the rest of the talk?
Right now, there are no questions, Ali. If anyone has a question, that can write that into the chat. Okay, I'll be reading them to Ali.
Perfect. Thanks, Maria.
Here, there is a question about weights. Could you elaborate on that?
So what is the question exactly?
The question is just weights.
So there is one scenario I'm gonna get into that you can assign weight. So you can use confidence as weight within the optimization process, within the loss function. I'm gonna get into that if you mean that. Okay,
the question is, can you simply use weights in training?
Yeah, we can. And I'm going to get into that, why we couldn't do that in our problem. That's an amazing question, because that's something comes to my mind for the first step. Awesome. So let's get back to our problem. So we want to do drug-target interaction prediction. We had Matchmaker. So let's review Matchmaker. What we had was millions of data points, and we had features from ligands and features from pockets of proteins. We put them together and we try to learn from them. But the question that we wanted to tackle, the problem we wanted to tackle, was to benefit from higher quantity and higher quality. Okay, so let's see the possible scenario for learning across label confidence distribution. The first solution is identifying best or optimal cutoff in the label confidence distribution. So this is our confidence distribution, which we have label confidence in the x-axis, frequency in the y-axis, and this is a distribution of all the data points, schematic representation only. This is not real data, but it mimics real data, because usually the distributions of the confidence we have in different data sets is skewed. We have right skewed distribution. So the first solution is to identify best cutoff, optimal cutoff. So we use this cutoff, we throw out the left side of the distribution and use the right side of the distribution, which is high confidence. And we've done that. Other people have done that in our domain, because this is a traditional way of dealing with this problem. But there are two problems. There are two issues with this approach, or limitations, we can say. One, we are throwing out data. So we wanted to benefit from higher quality and higher quantity. Now we are only benefiting from higher quality, not higher quantity. The other issue is generalizability, because we know that whenever we try to optimize for hyperparameters, there is a likelihood that we are increasing overfitting, because we try to become better and better with every single hyperparameter, and then there's a possibility of overfitting. So that could happen. Okay, so that's one issue, because this cutoff could be considered as a hyperparameter. There is another approach, which we tried as well. So, and it's ensemble learning. So for ensemble learning, the concept is to not build models out of different features and build ensembles of features like we do in random forest gradient boosting, AdaBoost, and so, but to train, for example, multiple deep learning models using different parts of this distribution. And we can use inclusive or exclusive data for those models. So the data points could overlap in this distribution or not. And that's not a problem. We tried both. And it works, although not as good as FTL that we tried later, but it works. The problem is computational cost. We are not talking about only paper publication. We are talking about business application. And in business, when you are doing ensemble learning and you have an alternative, in ensemble learning setting, you are increasing your computational cost. And that computational cost will increase the cost in dollars, because you have to use those models. Even if you dismiss the training cost, when you deal with clients and you want to predict something for them, you have to predict 10 times for every single data points to come up with the ensemble output, okay, with the ensemble prediction. And that was not applicable for us. And the third scenario, which our friend asked me, is about weight assignment optimization. It is an amazing approach. It worked in many applications, and there's no extra cost, which is in opposite to ensemble learning. So we don't have any extra cost. It is working in many other applications. Unfortunately, it cannot work for us because of this issue. So we have positives based on experiments and based on literature annotation. So combining all those, we have public data sets or some private data sets that we have all these annotations. So those are our positive data points. And we have confidence for those positive data points. But our negatives are not real negatives. And it's not only about us. This is something known in the field. So we have, imagine we have billion possible interactions. Okay, billion possible ligand and pocket combination. Okay, so we have, for example, 5 millions of them tested or annotated based on literature, but the rest of them, we don't know much about them. So what has been done previously, and we also benefited from it, is to consider the rest of them as random negatives. So we try to somehow, with some tricks, use those unknown data points as negatives, and we achieved high accuracy. So it was working. But the problem is those negatives, we don't have any confidence for them. So we have confidence for positive data points. We don't have any confidence for negative data points. And that's a problem, because now we cannot easily combine them within the loss function and do the weight-based optimization process. This is an amazing approach. Unfortunately, it didn't work for us. So, and just let me clarify, these are limitations for these approaches. It doesn't mean that they are bad approaches. They are amazing approaches, depending on the application you have, depending on whatever problem you want to solve. But they were not the best. So we tried the first approach and the second approach. The first approach was the initial trial. We wanted to get better. So it means that it was not a bad approach, just we wanted to get better. And the second approach, we had business limitations. So again, it doesn't mean that it's a bad approach from scientific perspective. It didn't work for us from business perspective. And the third approach, because of some limitation in the data set, we couldn't use. So any question?
Yeah, Ali, we have a question here. How do you obtain and validate the confidence labels? And could it be subjective or inconsistent?
So let me understand the question. So if you mean for the confidence that we get from the public data set, there are different ways. So that we have experimental measurements, and we have different levels of confidence on the measurements, or sometimes there are continuous values. And because we wanted to come up with classification, because of our business application, we had to somehow transform those continuous values to confidence. And the other thing is some of the labels are based on literature, and not necessarily we have same level of confidence based on literature. And there are other ways also for annotating drug-target interaction that results in different levels of confidence.
So yeah, the second question from that same person was if it's subjective or inconsistent. I think you answered that. Yeah. Another question was, how large is the space? Does it include all proteins?
So we try to get into all proteins, but the thing is, the whole space is all proteins for sure. But the positive space, the ones that we have data points for, it's not all proteins necessarily, because not all proteins have been tested. Usually the proteins have been tested that are somehow associated with the disease. Because imagine you're a pharma company or you're an academic lab. Why do you want to do random drug-target interactions? So there should be a target of interest. And those targets don't cover the whole space. But we are benefiting from whole space, considering the negative and positive data points together. Yeah.
Another question, how do you define binding pockets?
So we have some approach. Some of them are proprietary, and I cannot get into the details, but some of those pockets have been maybe reported, and we have other ways to identify potential pockets. and then use them in our framework, in our platform.
Another question. What about using the second approach and then training a new neural network to predict the results of the neural network ensemble?
So I mentioned the second approach is amazing. The only limitation, this is actually the approach, this ensemble or even a stacking approach has been used in Kaggle competitions. So many Kaggle competitors won Kaggle challenges based on stacked models. But the problem is there's a business limitation, because when you have multiple models and then use another model on top of it, you have to train all these models. And when you want to predict something new, again, you have to predict for that data point using all these models, which means that your computational cost is minimum maybe 10 times more. And that's a limitation. So that's a business limitation. When we get into business, the goal is not only to get better. So the target goal is not about getting a better performance. It's about getting a better performance while not losing much on the computational and business cost. So the ultimate goal is to do everything free with 100% accuracy. So think of the ideal case this way. So whenever we get closer to that point, it is better. So here we were gaining on the performance, but we were losing in the computational cost. So Maria Elena, if you don't mind, let me continue to make sure we don't have any time limitation, and then we can get into the rest of the questions. But those are amazing questions. Thanks for asking, guys. So let's look at the problem from another perspective. So we have a confidence distribution. And the question is, could we learn from all the data? So high quantity, but in average lower quality, and then continue training within the higher confidence part of the distribution. So lower quantity, but higher quality. Does it remind you of something? Maybe. It is transfer learning. So it is related to the concept of transfer learning. What we have done previously for transfer learning was to develop a machine learning model, a deep learning model, train it on a reference task, for example, ImageNet, millions of data points, and then bring that information, either the whole network or only the embeddings that we learned in that reference task, and bring it in another target data set, target task data set, and either use those embeddings with another machine learning model or somehow continue training the main model and then try to predict for target task. Here we change that. Instead of having a reference task and target task, we have same task but different levels of confidence for the data points. So somehow we mimic this process by considering all the data as a reference task and higher quality part of the data as the target task. So we are training on all the data, and then we are transferring that knowledge to higher quality part of the distribution and data to become better. And we could get better. So let me get into the model visual. It's called filtered transfer learning. And the concept, as I mentioned, is to learn from all the data or majority of the data. And in a stepwise manner, continue training, throwing out the low confidence part of the data and getting to high quality part of the data. So we are throwing out data, but we at least saw each data point once. So we are benefiting from quantity, while by throwing out the data in a stepwise manner, we are benefiting also from quality. And it worked. So imagine this is a distribution we have, and we have two-step FTL. FTL stands for filtered transfer learning. So we are learning from the orange part of the distribution, and then we continue training our neural network model, deep learning model, on a step 2. So this is the label confidence score on the x-axis. I'm talking about the left histogram. I'm not sure if you have my cursor, my mouse on this screen, but the left histogram has label confidence score on its x-axis and frequency on the y-axis. So we train on the first step, and then we continue training on the second step. So the two other plots, diagrams in this slide is for loss and accuracy. But let me explain this dashed line. This dashed line is the best model we could get using individual cutoff. So the first approach, if you remember. So considering, for example, only this red part, only this orange part, or many others. So we did hyperparameter optimization, and this dashed line was the best performance we could get in the loss and also in accuracy. And as we can see here, going from first step to second step, we have a jump in performance. So loss decreases, accuracy increases, perfect. So this is exactly what we wanted. And similar to weight assignment approach, we are not increasing computational cost. So these dashed lines was trained on the same number of epochs. So similar scenario, no increase in computational cost, but we could get a better result. But the question is, so we were curious to see what's going on in our neural network model. So we have, sorry again for the blurriness, I'm not sure what happened to my presentation, but what we have here is a neural network model. Imagine we have a simple few layers neural network. And the question is, when we go from first step to second step in a two-step FTL, it could be three-step FTL, from first step to second step and then second step to third step, what happens to the weights of these layers? Okay, are these ones, the initial layers, change drastically, or these ones change drastically? And if you are a deep learning person, you expect that these ones maybe should be the ones that change drastically, and that was the case. So in the first few layers, what we see is not much change on the weights. So this is just quantification distance between the weights of each one of these layers between first step and second step. And as we can see here, we don't have much change. But if we go to the last layers, we see a drastic change in the distance between the weights, which means that when we go from one step to another, these first layers are fine. So the embedding identification from the raw features, from the original features are fine. But how we use these embeddings in the rest of the networks to get into the classification in the last layer is problematic. Not problematic, we could become better at it. And that's how FTL works. And that's why FTL works better than the individual cutoff model. So based on our results, we showed that actually FTL works better than individual models, and we could achieve high accuracy and low loss using FTL model. And we believe it is applicable to other industries as well. And similar to weight assignment approach, there is no extra computational cost, and it's just a matter of try. And the implementation is also very easy because you can just go for multiple step training your model. Just you have to build your data set in that hierarchical process. So this is our paper. You can find it in archive, and I'm going to present it also as part of ICMLA this year in December. And thank you for your attention. I would be happy to answer any question you have.
Hi, Ali. They're asking if the slides are available for download.
These slides are available. I can share it. It's just a matter of asking TMLS folks how you can get access to it. If you want to get access directly from me, you can approach me on LinkedIn, and I would be happy to share them.
Okay. Can you share the link to your paper?
Yes. So I can share that as well. So it is called filtered. So let me see if I can put it in the chat box. So here, so learning across label confidence distribution using filtered transfer learning. So search for this now, and it should be the first few links. It's in archive.
No? No questions in the chat.
Thanks, Marielena, and thank you guys for paying attention, and I hope you enjoyed it.
Okay, guys. Thank you, Ali.